Quiz. Who said the following? The study of mechanics is eagerly pursued by all those interested in mathematics. What's the source of that quote? And here's another one. We attack mathematically everything in nature. Who said these things? Surely it's after Galileo anyway, right? He is the one who invented the mathematization of nature, so must be past that point, right? No. The quotes are from Pappus and Iamblichus, the Greek authors, ancient authors, well over 1,000 years before Galileo. Much modern scholarship would have you believe that such attitudes never existed. This is what you get if you read too much Plato and Aristotle and not enough mathematicians. In Plato, for example, mathematics is purer than snow. To apply to the physical world is to defile it. So that's quite an obstacle to science. If you glorify pure and abstract thought as the only worthwhile pursuit of rational beings, and you deride empiricism as fit only for unphilosophical beasts, then you're not going to get a whole lot of science done. Aristotle too has many teachings antithetical to proper science. There's his big book on physics, so-called, which is really metaphysical philosophy. Aristotle, he doesn't care about the phenomena or laws of motion. Instead, he cares about pseudo-profound philosophy puzzles like, does any motion have a cause? Or does motion presuppose the existence of a cause of that motion? And so on. And, oh, by the way, there are 4 different kinds of causes, you see. There's the efficient cause, the material cause, and blah, 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 whatever the other ones are. I mean, who cares? And so you can sit around and split hairs about that all day long. So that's typical philosophy, boilerplate stuff. Obviously a completely wrong turn on the road to science. So that's Plato and Aristotle in a nutshell. And if that's all you know about Greek scientific thought, then Galileo is a breath of fresh air, sure enough. But Plato and Aristotle do not speak for the Greeks. You don't get a very good idea of 20th century science by reading Sartre and Heidegger. And likewise, if you want to understand the Greek scientific thought, forget about Plato and Aristotle. In mathematical subjects, these people are derivative commentators at best. There is zero evidence that those Platonic and Aristotelian ideologies that I outlined had any influence whatsoever on any mathematically competent person in the classical and Hellenistic eras of antiquity. People often refuse to accept this, leading scholars. Their entire worldview is centered around the assumption that Plato and Aristotle are the alpha and the omega of Greek thought. Any suggestion to the contrary, they will fight with tooth and nail as if their life depended on it. Which, in fact, it kind of does, as I explained before. But to take Aristotle's ultra-philosophical physics as the state-of-the-art of Greek science is ridiculous. It's like saying that Wittgenstein was a leading 20th century quantum physicist. Read the mathematicians if you want to know what was really going on. We know for a fact that even Aristotle's own successors as heads of his own lyceum departed right away from his teachings on a number of scientific questions, and that's philosophers from his own school. So just imagine how little the mathematicians cared about Aristotle's ideas. Only much later, in the Middle Ages, there was a time of vastly lower intellectual quality. Only then did people come up with this imbecile notion of taking Aristotle to be an authority on physics, which is just ridiculous. But okay. Enough ranting about that. Now, what I would like to focus on is some actual Greek science. Let's think about some of Galileo's main results and investigate whether there were anything like those things in Greek times. Let's consider falling bodies. The laws of motion of falling bodies, that's a big Galilean triumph, isn't it? Well, not so fast. Maybe the Greeks already knew those things. We don't know, really, because a huge part of the Greek scientific corpus is lost. It has been burnt down in various library fires and whatnot, or just disintegrated and discarded. It was a fragile thing. those works, they had to be hand copied over and over to survive. Just think today about books from the 19th century and what state they are in now. And they're already falling apart. So ancient Greek works, they had to beat long odds to make it to the modern age. Take Euclid's Elements, for example. The oldest manuscript we have of Euclid's Elements is closer to us in time than to Euclid. From ancient times themselves, we have only the tiniest scraps, like a quarter of a page here and 3 lines there. Basically nothing from that time. And so the Greeks, that was a long time ago. How many of the books that we print today are going to be around in more than 2,000 years? Not many, I bet. But we know something about what was lost through references in other works. And as far as the science of falling bodies is concerned, we have some very intriguing indications. We know for a fact that Strato wrote the treatise on falling bodies. This treatise did not survive, but here's what we do know. Strato was an avid experimenter. To prove that falling objects speed up, he said, pour some water slowly out of a vessel. At first, it flows in a continuous stream, but then further down, its fall, it breaks up into drops, or kind of a trickle. And this is because the water is speeding up. The water, it's kind of spreading out as it falls, like cars let loose on a highway after a congested area. Here's another example that Strato used. Stones dropped into a sand bed from various heights. The stone, it makes craters of different depths depending on the height fallen. So again, it shows that the thing is picking up speed as it goes, just like the water drops. And did Strato make numerical measurements of this, of the sand craters, and some other way that he quantified the falling bodies? Maybe, who knows? And here's another guy who wrote on falling bodies, Hipparchus. That's an author who commands respect. Probably he was the greatest mathematical astronomer of antiquity, though, I mean, his works are lost, but we still know this. Certainly he was a way better mathematician than Galileo, that's for sure. So we know that he wrote a treatise on falling bodies, which is lost. Of course, he didn't follow Aristotle's ridiculous theory of falling bodies. In fact, a commentator on Aristotle explicitly says Hipparchus contradicts Aristotle regarding weight. But what exactly did Hipparchus say? The indications are that he argued that weight depends on distance from the center of the earth, and he seemed to have been engaged in questions like if there was a tunnel through the center of the earth and an object fell down into the tunnel, what would happen as it approached the middle and stuff like that. So the superficial commentators that through whom we know about these works, they have picked up on these striking aspects, thought experiments, those things that can be presented in a kind of gimmicky way in isolation. So in the original, they would surely have been incorporated in a mathematical treatment. And these things are very much in line with 17th century physics, dropping a stone into sand, thinking about how gravity varies on a superterrestrial scale inside the Earth. That is literally exactly what scientists spent a lot of serious effort on in the 17th century. So these are the facts that we know then. Greek scientists, who were excellent mathematicians and keen experimenters, wrote several lost treatises specifically on the subject of falling bodies. What are the chances that these included good chunks of so-called Galilean science? Maybe, for example, Galileo's law of fall? These chances are appreciable in my opinion. It is squarely within the realm of possibility and then some. Here's what the modern scholar says about Galileo's law of fall. The ease of stumbling upon this discovery renders it highly improbable that natural philosophers had ever searched for the law of fall before the 17th century. Yeah, maybe, or either that or else they did search and they did find it. If it's so easy to stumble upon, what are the chances that these very sophisticated, first-rate minds who wrote entire treatises on this exact subject somehow missed it? That is certainly food for thought, to say the least. So the law I'm talking about here is the one that says Galileo's law of fall. I mean the law that says that the acceleration of a freely falling object is constant, or equivalently the velocity is proportional to time, and the distance is proportional to time squared. Motion on an inclined plane is closely related to this. A ball rolling down a slope, it's basically a slow motion version of falling body. The ball, it will acquire the same speed through rolling as it would have in free fall when it covers the same vertical distance. So as we would say today, using anachronistic terms, since all balls covering the same vertical distance trade in the same amount of potential energy, they get the same amount of kinetic energy out of it at the end, so they have the same speed at the end of this process. Anyway, the slow motion version of falling is easier to deal with experimentally. Let me quote again Stillman Drake, the Galileo scholar, and he says, "In a way, it is surprising that the law for the spontaneous descent of heavy bodies had not been recognized long before the 17th century. Measurements sufficient to put the law within someone's grasp are quite simple. Equipment for making them had not been lacking: a gently sloping plane, a heavy ball, and the sense of rhythm with which everyone is born." The sense of rhythm, that's like a natural clock. You can tell when a musician is off beat. This is an innate skill that we can use to verify the law. No stopwatch is required for this. So just you get your inclined plane, you put markers at the intervals that the ball ought to cover in equal times, according to your hypothesized law of fall, and then you put little bells in all those positions and you roll the ball down the slope. Now, do the bells ring at equal intervals or unequal intervals? It's quite easy to tell. In fact, I did this experiment for your benefit, and I'm going to play it for you. I used a very simple and primitive setup. I just used some stuff I had around the house. For my inclined plane or ramp, I found a suitable piece of wood in my basement. It used to be part of some furniture or other. And then I took a kitchen knife and I cut some markings into it at the places where the rolling ball should, the intervals that the rolling ball should cover in equal times according to the Galilean law of fall. And that just means you put the measuring tape down and you mark at all the square numbers. So I made marks at the distance 4, 9, 16 and 25 units from the starting point. Those are the squares. Any unit, there's no need to know anything about like a gravitational constant or anything like this for these purposes. Just put the ruler down, make the marks at the square numbers, and that's it. Okay, so I did this, and then I put the ramp in position just on my living room coffee table, and I got myself 4 wine glasses that I put along the ramp at the positions of these markings that I made. And I just, propped them up with some books or whatever as necessary to put it all in position. And it happened that I had a glass marble as well as the ball that I needed, which happened to fit. So I positioned everything in such a way that this marble would, as it was rolling down the ramp, it would just touch each of the wine glasses. So let's see, I'm going to play it for you now. And the idea is then that as I play it, you're supposed to hear 4 equally spaced clinking sounds. Let's see if you're convinced. It worked pretty well, I'd say. This thump at the end, that is the marble is crashing into a bundled up t-shirt that I put at the end of the ramp to catch it. And I also made some recordings for comparison with the glasses in the wrong position. So I put the glasses the wine glasses at roughly equally spaced intervals instead of spaced like the square numbers. So equal distances now instead of equal time intervals, which was the previous setup. So I will play that recording as well, and then we'll see if you can spot the difference, if you can hear it with your natural sense of rhythm. I think the difference is pretty clear. Considering that I threw this experiment together very sloppily in about 10 minutes, I'd say it's viable, it's easy to build a quantitative theory of falling bodies this way. Obviously, it will be easy to improve the accuracy of the experiment a lot from my extremely primitive setup. The way I did it, the marble kind of whacked into the wine glasses pretty good there. Probably slowed it down, perhaps a non-trivial amount, and so on. So if I was doing it for real, obviously I would use a heavier ball, a longer ramp. Mine was like a meter or something. And for the markers, I would use like tiny bells or something that's not heavy enough to impact the ball or marble as it's rolling. But I think even the way I did it kind of worked. And actually, I made a number of takes with each of these configurations, so I figured I'll play a couple more of them as a kind of blind test. So we'll see if you can hear which are the correct configurations with the equal time intervals and which are the bad ones with the unequal time intervals. Okay, so here we go. You tell me which is the right one and which is the wrong one. That was one of the good ones. The ones with equally spaced sound is what you are supposed to have heard that situation. Here's the next one. That was good again. You should have heard equally spaced sounds that time. Next. That's bad, unequal time intervals. Next. And that was a bad one with the unequal time intervals. Well, those are the clips. Judge for yourself how realistic you believe it is to do quantitative science based on those experiments. We don't know if the Greeks did something like this. There's no evidence that they did, although they certainly could have. Anyway, let's put that question aside. There's a more general point that I want to make here. This stuff about the inclined plane, it's very simple. The law is simple, the mathematics is simple, the experiment is simple, the idea is simple. You can explain everything to a child. If Galileo was the first to discover stuff like this, it must be considered a revolution or breakthrough of a conceptual nature, as opposed to a mathematical one, because mathematically it's completely trivial. Actually, this goes for almost all of Galileo's so-called achievements. So this suggests an underlying question. Are there conceptual revolutions like that? Is the history of science a story of conceptual revolutions that made previously unimaginable things suddenly obvious? Some people are very willing to accept this. Many scholars, in fact, are happy to say yes. It's quite fashionable even, I would say, to insist that this is the case. Historians make a big mistake here, in my opinion. They start from a reasonable premise. They observe that those who have little or no expertise in history often interpret historical episodes in a naive way. These historical beginners, they take current ways of thinking for granted. They kind of small-mindedly interpret past thought in terms of these narrow categories of current knowledge. That's a massive mistake, of course, and it's very stupid because it defeats the whole purpose of studying history in the first place, namely that history can show us other perspective, other ways of thinking, and broaden our horizons. So that's all fine and well. The modern historians, they're very much correct in condemning that type of mistake. However, they go too far. They think to themselves, well, since it's bad to involve too much current ways of thinking when looking at the past, the best historian must be the one who does the exact opposite of that. That is to say, the best historian must be the historian who always emphasizes conceptual differences whenever possible, who always blows the tiniest indication of differences way out of proportion as if it was a huge deal. Now, since this is the opposite of the naive approach that I mentioned, it must be the pinnacle of sophistication, right? That's how many historians seem to reason. In my opinion, that is of course a bad idea. It's just as naive as dogmatic as the erroneous mentality it was supposed to counter. But, well, it's not my purpose here to criticize this in general, only to consider what it means in the case of Galileo. I said I could explain this thing with the rolling ball and the law of fall to a child, by which I mean any child, modern or ancient. This is what the modern historians are eager to deny. They do not believe in such universalism. They say, no, the Greeks lived in a different conceptual universe. Their way of thinking is just fundamentally, qualitatively different from ours. Even the most obvious and evident thing to us may very plausibly have been completely outside of their conceptual sphere. They couldn't even think it because the way they approach the world is just inherently and profoundly different from ours. So Galileo's status as a scientific innovator stands and falls with our willingness to accept this radical relativism. His discoveries are so basic and obvious that the only way to consider them profound is to maintain that they were once not basic and obvious. In other words, that they are fundamentally different in character from anything the Greeks were doing, for example. If we think there's only one common sense and that mathematical truth is the same for everyone, then we are strongly inclined to see Galileo's achievements as quite basic. We are strongly inclined to think that the works of, for example, Hipparchus on falling bodies was probably very similar to what 17th century authors said on the same subject. On the other hand, if we reject the very notion of a universal scientific common sense, then we are primed to think that Galileo opened up an entirely new world with his style of science. So, studying Galileo is a mirror to these much larger questions. Either you are a cultural relativist and you think Galileo was a revolutionary, or you think mathematical thought is the same for you and me and everybody who ever lived, and then you think that Galileo was just doing common sense stuff. Now, those are the two possibilities. You have to pick sides. You can't mix and match. You can't have both mathematical universalism and Galileo being a revolutionary. These two basically contradict one another. That is my point. So, once again, Galileo is at the heart of fundamental questions about history, which is all the more reason to study him in detail, which is exactly what we are going to do. Next episode, it's Into the Weeds on Galileo's work on falling bodies. Thank you.